It's late. The glow of the monitor is probably the only light in the room right now. You're looking over your code base, and maybe you're thinking about how your system actually sees the physical world.
Yeah, that physical translation is always the tricky part, isn't it?
Right. Because usually when we talk about a computer vision system detecting something, there's this expectation of a crude, almost blunt force approach. Like you draw a bounding box around a car, your system says, hey, there's a car somewhere in this rectangle.
And for a long time, we just sort of accepted that as good enough. I mean, it was a functional approximation for an era constrained by compute.
Exactly. It gets the job done if you just need basic counting or like a general location of an object on a screen. But then you actually look at the math of that bounding box.
Ooh, the math is rough.
It is. Roughly 40% of the pixels inside a typical bounding box are just background noise. They aren't the object at all. It's the sofa behind the cat.
Or the sliver of pavement right next to the tire.
Right. And if you're building systems that actually matter in the physical world, like medical imaging or autonomous driving, that 40% noise is completely unacceptable. You don't need to know a tumor is somewhere in a box. You need to know exactly which cells are cancerous, pixel by pixel.
The field has definitely outgrown those blunt rectangles. Moving from a general approximation to, absolute spatial certainty, that's the defining architectural challenge we're unpacking tonight.
Welcome to tonight's deep dive. Our mission today is exploring the architecture of image segmentation. We're looking at a stack of notes and architectural breakdowns on how models achieve absolute pixel-perfect understanding of an image.
Which is fascinating, because if you're engineering these systems, you really need to understand how we got from these broad boxes to pinpoint accuracy.
So let's just jump straight into the material because, labeling a pixel sounds super simple, but it means completely different things depending on what your system is actually required to do.
Right. To understand how these models label every pixel, we first need to define the exact problem space. The field uses these terms very precisely.
And confusing them will probably lead to serious architectural misunderstandings later on.
Absolutely. There are three distinct flavors of segmentation we need to establish before looking at the code.
Okay, let's unpack the spec. What's the first flavor?
The first is semantic segmentation. This is where the system labels every single pixel in an image with a class, but, and this is the key, it does not distinguish between different instances of the same class.
So wait, if your autonomous vehicle's camera sees like 3 people crossing the street?
All of those pixels across all 3 bodies simply get the label person. You know where the person pixels are, but the system doesn't inherently know that they belong to 3 distinct human beings. It just sees a continuous region of human class pixels.
Okay, that makes me think of coloring a map. If you're doing semantic segmentation on a map of the world, all the water is blue and all the land is green.
That's a great way to picture it, yeah.
You can clearly see the continents, but you can't tell Africa from South America just by looking at the green pixels because they all share the exact same land label.
The map analogy works perfectly, but think of it strictly from the machine's perspective. It's purely a per-pixel classification problem. The machine doesn't see continents or oceans.
It just sees a massive array.
Right, exactly. A massive array where every coordinate is independently evaluated and tagged blue or green. Now, the second flavor goes a step further to solve that specific limitation.
Which is instant segmentation.
Right, instant segmentation. Here, the system not only labels every pixel, but it actually distinguishes between different instances of the same class.
So those 3 pedestrians crossing the street aren't just a single blob of person pixels anymore.
No, the network assigns them distinct identities. It's like person 1, person 2, and person 3.
So sticking with the map analogy, this is where you give every single individual country its own unique color. You know exactly which pixels belong to France versus Spain, even though they are both technically land?
Precisely. You know exactly which pixels belong to which specific entity. And finally, we have panoptic segmentation.
The Holy Grail.
It really is considered the holy grail of the vision field right now. It combines both semantic and instance segmentation to give you a complete, unified understanding of the entire scene.
So it handles everything at once.
Yeah, it handles what we call stuff. So uncountable amorphous regions like the sky, the drivable road, the grass using semantic segmentation. And it concurrently handles things, countable, individual objects like cars and pedestrians using instance segmentation.
I really love the analogy in the source material for this. They compare it to text. A bounding box is like taking a pen and, circling a whole word on a
You
page.
capture the word, but a lot of extra junk, too.
Right. You're capturing the letters, sure, but you're also circling the white space, maybe the bottom of a letter from the line above. But panoptic segmentation is like using a highlighter perfectly over just the ink of the letters themselves, nothing extra.
That's it, exactly. But achieving that level of highlighting requires immense computational finesse. I mean, if panoptic segmentation is the end goal, highlighting everything and all the stuff the immediate engineering challenge becomes, well, how do we actually build a network architecture capable of outputting that?
Because the standard image classification networks were fundamentally incapable of this, right? Just because of how they processed spatial data.
They really were. If you look back at networks like VGG or AlexNet from the early days,
Oh yeah, they were incredibly good at telling you what was in the image, but they completely destroyed the where.
because they end with fully connected layers. Those final layers take the beautiful, rich, two-dimensional spatial grid of the image and mathematically flatten it out into a single, one-dimensional vector.
Just completely crushing the geometry.
Right, and the entire purpose of that operation is to spit out a single probability score for a class label, like cat. To do segmentation, to understand where the cat actually is, the first major plumbing change the field had to make was ripping those fully connected layers out entirely.
Just deleting them.
Pretty much. This paradigm shift happened around 2015 with FCNs, or fully convolutional networks.
Fully convolutional, so they just swapped the fully connected layers for more convolutional ones. It seems like a pretty obvious fix in hindsight.
Yeah, by replacing the fully connected layers with one-by-one convolutions, the output preserves its two-dimensional spatial structure. Instead of producing one single label for the whole image, the network produces a spatial heat map of class probabilities.
But as any engineer listening can probably guess, solving one architectural bottleneck usually introduces a massive bug into the pipeline somewhere else.
Always. In this case, it was the downsampling
Which
property.
honestly, I always found counterintuitive. Like, why shrink the image if you're just going to need the high resolution data later?
Well, classification networks inherently use pooling layers and strided convolutions to progressively shrink the spatial resolution of the image. They have to do this to build a hierarchy of features and to expand the receptive field.
So it can see the bigger picture.
Right. You want the network to understand the abstract, high-level concept of a cat, regardless of where it is on the screen. But by the time a 512 by 512 pixel image passes through all those downsampling layers to gain that semantic understanding, it gets crushed down to a tiny 16 by 16 feature map.
Which is completely useless if you're trying to draw a pixel-perfect boundary around a tumor. I mean, a 16 by 16 grid is basically a blurry mosaic.
It's far too coarse. So the FCN engineers had to find a way to upsample, to literally reverse the process and mathematically blow that 16 by 16 map back up to the original 512 by 512 resolution using transposed convolutions.
But when you inflate a compressed feature map, you've permanently lost the fine edges, haven't you?
Exactly. The network knows there's a person generally in the top left quadrant, but the exact contours of their fingers or, the curve of their shoulder, those are gone. The spatial data was destroyed during downsampling.
So how did they get those edges back? The notes talk about skip connections here, and I'm really trying to wrap my head around it. It feels a bit like painting a portrait.
A portrait. How
Yeah.
so?
Well, if you're an artist, you don't just start painting individual eyelashes in the corner of the canvas. You start with the rough sketch, the deep features. You say, okay, the face goes here, the shoulders go here. That's your composition.
Right, the general semantic layout.
Yeah. But to make it look real, you need to go back and add the fine details, the exact curve of the jawline, the sharpness of the collar. You have to somehow fuse those two things together.
That's actually a brilliant analogy. Skip connections are the mathematical equivalent of fusing that rough sketch with the fine details. They take the high-resolution feature maps from the early layers of the network, the layers that haven't been downsampled yet, and still know exactly where the sharp edges are.
Okay.
And they literally concatenate them with the deep, upsampled, low-resolution layers that know what the objects are.
Okay, so FCNs introduced this skip connection idea to patch the downsampling problem, but it sounds a bit, I don't know, ad hoc. It's still fundamentally a classification network trying to do a segmentation job. How did the field formalize this zoom in, zoom out process into an architecture actually built from the ground up for this?
That brings us to what is arguably a masterpiece of network design, UNet. proposed by Olaf Ronneberger and his colleagues, also in 2015. They took this encoder-decoder structure and those skip connections and built a beautifully symmetric architecture shaped literally like the letter U.
I'm looking at the architectural diagram of this in our notes, and it really is elegant. Walk us through the U, step by step.
Sure. Imagine the left side of the U is the downward path, the encoder. The image passes through convolutional blocks and max pooling layers. With every step down this path, the spatial dimensions of the image are halved, say, from 512 down to 256 down to 128.
Okay, getting smaller and smaller.
But simultaneously, the number of feature channels the depth of its understanding, like filters looking for edges, textures, or specific shapes, is doubled.
Oh, interesting. So the network is shrinking the physical size of the data, but massively growing its semantic richness.
Exactly. It hits the bottom of the U, the bottleneck, where it has maximum abstract context but minimum spatial resolution.
So down there, it knows absolutely everything about what is in the image, but it's effectively blind to exactly where any of those things are drawn.
Right. Then it begins the upward path, the decoder, climbing the right side of the U. At each step up, it uses transposed convolutions to double the spatial dimensions and halve the feature channels, upsampling back toward the original resolution.
But the absolute genius of UNet, the reason it is so iconic,
Is the systematic skip connections.
right, bridging the left and right sides of the U at every single spatial level.
Yes. So at the same time it's expanding the image back up to 256 by 256, it's reaching across the aisle to the encoder at that exact same 256 by 256 level and saying, hey, before you compress this, where were the crisp edges?
That is so clever. The decoder doesn't have to mathematically hallucinate the fine details from a compressed state.
Exactly. It simply concatenates the upsampled abstract features from the bottleneck below with the pristine, high-resolution spatial features passed directly across the U. This architecture is so remarkably efficient that it was originally designed for biomedical imaging, a domain where labeled data is notoriously scarce.
Right, because having an expert pathologist sit there and manually color in individual cancerous cells pixel by pixel for thousands of images is just impossible. It takes hours per image.
It does. And UNet achieved world-class results on tiny data sets. We're talking as few as 30 labeled images.
Wow, only 30.
Yeah, just 30. Because its structural prior, the very shape of the network, was so strong for spatial translation, it's racked up over 70,000 citations. It remains one of those foundational papers in computer science history.
Here's where it gets really interesting, though. UNet is this elegant shrink it down and blow it back up approach. But let's look at the engineering constraints. Shrinking an image requires losing data, and expanding it requires heavy compute. What if a system is highly constrained? Or what if you just, didn't shrink the image at all?
Well, downsampling is inherently destructive. If your system relies on retaining the absolute highest fidelity of the original image, you can't just use standard convolutions and max pooling. That led the field to an alternative approach: dilated, or matrice, convolutions.
I struggled a bit with this concept in the notes. How do you look at a wider area of an image to gain context without actually shrinking the image to fit into your filter?
Okay, think about a standard convolution filter. It looks at a tight little 3x3 grid of immediately adjacent pixels, 9 pixels total.
Okay, a little square.
Right. A dilated convolution artificially introduces spaces between the pixels it samples. So if you use the dilation rate of 2, the filter still looks at a 3x3 grid, but the pixels it pulls from are spaced 2 pixels apart.
Oh, I see.
So it physically covers a 5x5 area of the image, but it's still only doing the mathematical operations for 9 pixels.
Oh, it's like looking through a lattice fence. You're standing at the fence, and you can see through the gaps. You get a sense of the whole yard, the broader scene, but you're only actually sampling reality at regular intervals through the wooden slats.
That captures the mechanism perfectly. By increasing the dilation rate layer by layer from 2 to 4 to 8, the network's receptive field grows exponentially. It can eventually see the whole image context without ever once downsampling the spatial resolution.
That's incredibly smart.
It is. This lattice-like sampling was the foundation for Google's DeepLab family of models. It proved you could achieve incredible semantic segmentation without suffering through the destructive bottleneck of a UNet.
Okay, so dilated convolutions handle the what is everything semantic part really well while preserving resolution. But earlier we talked about panoptic segmentation, finding both the amorphous stuff and the specific countable objects. I want to look at how the field solved that instance segmentation side.
The things part of the equation.
Right, because we've covered object detection previously with faster RCNN. If fast RCNN was already so good at finding individual cars and drawing tight boxes around them, why was it suddenly so hard to just tell the network to output a mask instead of a box? I mean, a box is just 4 coordinates, right? X, Y, width, height. Filling it in should be trivial.
It sounds trivial until you look at how the network maps those bounding box coordinates back to the internal feature map. The answer to why it broke is a highly technical fix implemented in Mask RCNN, specifically addressing a mechanism called ROI align.
Let's get into the plumbing here. What was breaking under the hood?
So faster RCNN used an operation called ROI pooling to take the region it proposed the box around the car and map it back to the grid of the internal feature map so it could classify it.
Okay.
But when it projected those continuous coordinates onto the discrete grid, it frequently landed between pixels. ROI pooling handled this by simply rounding the coordinates to the nearest grid cell. It snapped them into place.
Which introduces a quantization error.
Exactly. A severe misalignment, sometimes off by half a pixel or more. Now, if all the network is doing is outputting a bounding box that says car, being internally off by half a pixel doesn't really matter. The box is still generally around the car.
Right, a box is forgiving.
But if you are trying to output a pixel-perfect segmentation mask, that half-pixel rounding error at the feature map level is absolutely devastating. It completely destroys the boundary alignment when projected back to the original image. The mask just spills over the edges of the object.
So how did Mask RCNN fix the math?
The engineers introduced ROI align, which eliminated the rounding operation entirely. Instead of snapping the coordinates to the nearest grid cell, it used bilinear interpolation to calculate the exact, continuous value at precise fractional positions on the feature map.
By linear interpolation, so what does that actually mean in this context? Because I hear that term thrown around in computer graphics all the time.
Think of the feature map as a rigid grid. When the bounding box projection lands somewhere between the grade intersections, say at coordinate 4.5, ROI pooling would just aggressively round that to 4 or 5.
Right.
Bilinear interpolation looks at the 4 pixel centers immediately surrounding that 4.5 coordinate. It calculates the exact physical distance to each of those 4 centers and creates a weighted average based on how close the point is to each one.
Wow.
It mathematically hallucinated the exact subpixel value instead of forcing a rounding error.
That is wild. So they just did the microscopic math to say, no, we aren't rounding to fit the grid. We're interpolating exactly where this feature sits. And that tiny mathematical detail is what allowed them to accurately paint a mask over the object inside the box.
It proves that in segmentation, the macroscopic success of the architecture is entirely dictated by microscopic mathematical precision.
Yeah.
By fixing that subpixel alignment, Mask RCNN was able to add a completely decoupled mask prediction head alongside the class prediction head. It became the absolute workhorse of instance segmentation for years.
Okay, so we've got UNets zooming in and out. We've got Deep Lab looking through lattice fences. We've got Mask RCNN fixing half-pixel quantization bugs with bilinear interpolation. But as any software engineer tuning into AI right now knows, eventually, the transformers come for every architecture.
Always. The inductive biases of convolutional neural networks, the handcrafted feature pyramids, the carefully tuned dilated convolutions, they were the dominant paradigm of the past decade. But CNNs have a fundamental limitation.
They are too localized, right?
Exactly. A convolutional filter, by definition, has a local inductive bias. A 3x3 filter only looks at its immediate neighbors. To understand how a pixel in the top left corner of an image relates to a pixel in the bottom right corner, the image has to pass through dozens of convolutional and downsampling layers until those features are finally compressed enough to sit next to each other in the bottleneck.
Which, as we established earlier, destroys the high-resolution spatial data we desperately need for drawing the mask.
That is the ultimate bottleneck. Transformers change the paradigm entirely by replacing convolutions with self-attention. Self-attention allows every single patch of pixels to mathematically compare itself to every other patch in the entire image simultaneously, in a single layer.
So a patch in the corner can directly attend to a patch on the opposite side without waiting for 50 layers of compression.
Precisely.
And this is where we see models like SETR, SegFormer, and Mass2Former taking over, right? They just rip out the CNN encoders and drop in general-purpose transformer blocks.
Yeah, if you have enough compute and enough data, the learned global flexibility of attention mechanisms simply outperforms handcrafted CNN components. Which brings the field to 2023 and Meta's release of SAM.
The segment anything model, the sources repeatedly call this the GPT-3 of vision.
It is the first true foundation model for segmentation. SAM's architecture completely abandons task-specific training. You don't train a SAM model just to find cars and another just to find tumors.
It's all just one massive model.
Right. It consists of three distinct parts. A massive image encoder based on a vision transformer that processes the entire image, a prompt encoder that takes user input, and a lightweight mask decoder that combines the two to generate the final mask in milliseconds.
The prompt encoder is where I think SAM acts like a universal translator for segmentation. Just like a large language model translates a text prompt into code or poetry, SAM takes a prompt, which could be a literal mouse click on a pixel, drawing a rough bounding box, or even typing text.
And it mathematically translates that physical action into a vector.
Right. And the mask decoder uses that vector to output a perfect segmentation mask of whatever you pointed at.
It performs the zero-shot segmentation for objects and domains it wasn't even specifically trained on. The secret to this generalization isn't just the transformer architecture, though. It's the SA1B dataset. Well, Meta built a data engine, an iterative flywheel, where human annotators used early versions of SAM to label images. Those human-corrected labels trained a better version of SAM, which then helped humans label even faster. Through this loop, they generated 1.1 billion high-quality masks.
1.1 billion masks.
Yeah.
The scale of that is staggering. And now with SAM 2, they've pushed this architecture into video processing. So you click on a skateboarder in frame 1, and the model maintains a pixel-perfect mask of that skateboarder across every single frame.
Maintaining temporal consistency as they move through the scene, get occluded by objects, and reappear.
Which fundamentally changes the deployment landscape for these tools.
So it completely revolutionizes it.
So let's talk about that deployment. Where is this code actually executing in the listener's daily life right now? Because we've gone super deep into the architecture, but these models are running silently all around us in production.
They're deeply embedded in infrastructure you interact with daily.
Like, if you took a Zoom call today and blurred your background, a lightweight segmentation model was running locally on your machine, classifying every single pixel as you or not you at 30 frames per second.
And beyond video conferencing, autonomous driving perception systems are running panoptic segmentation to map drivable roads, track pedestrians, and classify traffic signs in real time.
Augmented reality glasses use segmentation to map the exact geometry of a living room at sub-centimeter precision, right? Ensuring a digital object can sit realistically on a physical table without clipping right through it.
Absolutely. Not to mention industrial agriculture. Satellites are running segmentation over entire continents to map crop types, monitor soil health, and track deforestation at meter-level resolution.
It's wild to think about the scale, but looking at the technical notes from the sources, there is still one fundamental tension the field hasn't entirely solved, even with transformers.
Yeah, despite all this progress, from FCNs to UNet to SAM, there is an inherent physical tension in the math. It's the permanent trade-off between semantic understanding and spatial precision.
Knowing exactly what an object is versus knowing exactly where its boundary is.
Exactly. Deep network layers with heavy downsampling or massive attention windows are brilliant at context. They know exactly what they're looking at, but they naturally blur the edges of the object.
And shallow networks.
Shallow network layers perfectly preserve sharp, crisp, high-resolution edges, but they lack the broader contextual awareness to know what edge they are looking at. Every single architecture we discussed today, skip connections, dilated convolutions, ROI align, self-attention, is essentially just a different engineering hack attempting to balance those two competing physical realities.
So what does this all mean for the engineer listening right now? We've gone on quite the journey tonight. We started with the crude 40% noise world of bounding boxes. We engineered UNets to zoom out for context and zoom in for precision. We looked through the lattice of dilated convolutions.
Fixed half-pixel quantization bugs using the bilinear interpolation of mask-RCNN.
Right. And we finally handed the keys over to transformers and SAM to let us segment anything in the world just by prompting it. Understanding how these layers actually interact, how spatial data is preserved, destroyed, or hallucinated is the absolute key to building whatever the next generation of visual tools is going to be.
I will leave you with one final thought to mull over until next time. We have spent this entire deep dive analyzing reality. We've dissected architectures explicitly designed to perfectly understand and segment existing pixels on a screen, but consider the implication of achieving that perfection.
Where does perfect analysis lead us?
Well, if a model knows mathematically, with pixel-perfect precision, exactly what constitutes the boundary of a face, or a road, or a sky, the next logical step isn't just analyzing reality, it's altering it.
Oh, wow.
If you have that level of foundational spatial understanding, you can combine it with generative adversarial networks, GANs, or diffusion models. You transition from an AI that just draws boundaries around the world to an AI that can generate photorealistic realities entirely from scratch within those boundaries.
From drawing perfect lines around what is to painting exactly what isn't. Something to chew on as you look back at that code base tonight.